According to the National Electrical Code Section 250.122c2, grounding electrode conductors can be run in the same raceway with supply conductors of the same system. This means you can run the grounding electrode conductor, or GEC, in the same conduit as the wires feeding your transformer. If you want an equipment grounding conductor, or EG, in the conduit, you'll need to pull a separate wire. The grounding electrode conductor connects the transformer to the grounding electrode system, while the equipment grounding conductor connects the transformer enclosure to the grounding busbar in the disconnect. These are two distinct conductors with different purposes. You should bond the conduit at both ends using a supply-side equipment bonding jumper, following Section 250.92 of the National Electrical Code. The bonding jumper should be installed between the grounding electrode conductor terminal in the transformer and the grounding electrode conductor terminal in the disconnect. This makes sure the conduit is properly grounded and offers a continuous electrical path to the grounding electrode system. Let's delve into the specifics of each of these aspects. Firstly, grounding electrode conductors. The grounding electrode conductor serves as the crucial link between the electrical system and the earth. Its primary function is to provide a low impedance path for fault currents to return to the source, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses. This connection to earth is vital for safety, preventing dangerous voltage buildup on conductive surfaces. According to the National Electrical Code, the size of the grounding electrode conductor is determined by the size of the service entrance conductors. Specific tables within the code, such as Table 250.66, outline the appropriate conductor size based on the size of the service entrance conductors. It is important to consult these tables to ensure proper sizing, which is critical for effective fault current management and overall system safety. Materials commonly used for grounding electrode conductors include copper and aluminum. Copper is favored for its excellent conductivity and corrosion resistance, while aluminum offers a more cost-effective alternative, although it requires larger sizes to achieve equivalent conductivity. The National Electrical Code specifies the allowable uses and installation requirements for these materials, ensuring that they meet safety standards. Secondly, equipment grounding conductors. Equipment grounding conductors, distinct from grounding electrode conductors, are dedicated to grounding non-current carrying metal parts of electrical equipment. This includes enclosures, conduits, and other metallic components. The purpose of the equipment grounding conductor is to provide a low impedance path for fault currents to return to the source, thereby protecting people from electric shock hazards. When a fault occurs, such as a live wire coming into contact with a metal enclosure, the equipment grounding conductor provides a path for the fault current to flow back to the source, tripping the circuit breaker or fuse and quickly de-energizing the circuit. The National Electrical Code mandates that all non-current carrying metal parts of electrical equipment be grounded. This requirement ensures that in the event of a fault, the exposed metal parts will not become energized, reducing the risk of electric shock. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. Table 250.122 in the National Electrical Code provides guidelines for selecting the appropriate size of the equipment grounding conductor based on the ampere rating of the circuit breaker or fuse. It is vital to adhere to these sizing requirements to ensure effective fault current protection. Thirdly, conduit bonding. Conduit bonding refers to the practice of electrically connecting metal conduits to ensure a continuous low impedance path for fault currents. This is crucial for maintaining electrical safety and preventing voltage buildup on the conduit system. When a fault occurs, the conduit system can become energized. Proper bonding provides a path for the fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. The National Electrical Code requires that all metal conduits be properly bonded to ensure electrical continuity and effective fault current protection. Various methods can be used for conduit bonding, including bonding bushings, bonding jumpers, and threaded connections. Bonding bushings are installed on the ends of conduits to provide a secure connection to the enclosure. Bonding jumpers are used to connect sections of conduit together, ensuring electrical continuity. Threaded connections, when properly tightened, can also provide a reliable bonding connection. Section 250.92 of the National Electrical Code specifically addresses the requirements for bonding service equipment. It mandates the use of bonding jumpers to connect the service equipment enclosure to the grounding electrode system. This bonding ensures that the entire service equipment is properly grounded and the fault currents have a low impedance path to return to the source. When installing bonding jumpers, it is crucial to use the appropriate size and type of conductor. The size of the bonding jumper is determined by the size of the service entrance conductors, as outlined in Table 250.66 of the National Electrical Code. The bonding jumper must be securely connected to both the service equipment enclosure and the grounding electrode system to ensure effective electrical continuity. Fourthly, supply-side bonding jumpers. Supply-side bonding jumpers are conductors used to connect the grounded conductor, typically the neutral, to the equipment grounding conductors on the supply side of the service, disconnecting means or source of a separately derived system. Their main purpose is to establish a lower impedance path for fault current to return to the source, aiding in the quick tripping of overcurrent protection devices like circuit breakers or fuses during a ground fault condition. In separately derived systems, such as those using transformers or generators, the supply-side bonding jumper is especially important. It connects the neutral point of the separately derived system to the metal enclosure of the source and to the grounding electrode system, ensuring a solid ground reference for the system. The size of the supply-side bonding jumper is determined by the size of the service entrance conductors or the derived phase conductors, in accordance with National Electrical Code Table 250.102. Selecting the right size is crucial for the jumper to effectively carry fault current. The jumper must be made of copper or other approved conductive materials and should be installed in a way that provides a low impedance path. Fifthly, grounding electrode conductor terminals. Grounding electrode conductor terminals are connection points where the grounding electrode conductor is attached to equipment, such as transformers, service panels, or grounding electrodes. These terminals must provide a secure and reliable electrical connection to ensure that the grounding electrode conductor can effectively carry fault current. The National Electrical Code specifies requirements for the construction and installation of grounding electrode conductor terminals. They must be made of corrosion-resistant materials and be suitable for the size and type of conductor being used. Terminals should be listed and labeled for grounding purposes, indicating that they meet safety standards. Proper installation of grounding electrode conductor terminals is essential for maintaining the integrity of the grounding system. Terminals must be securely tightened to ensure a low impedance connection. The surface where the terminal makes contact should be clean and free of corrosion to facilitate good electrical contact. Sixthly, transformers and grounding. Transformers are key components in electrical distribution systems, used to step up or step down voltage levels. Proper grounding of transformers is essential for safety and to maintain the integrity of the electrical system. Grounding the transformer involves connecting the transformer enclosure and the neutral point of the transformer winding to the grounding electrode system. This provides a low impedance path for fault currents to return to the source, protecting equipment and personnel. The National Electrical Code specifies the requirements for grounding transformers in Article 450. This includes sizing the grounding electrode conductor, bonding the transformer enclosure, and connecting the neutral point to the grounding electrode system. Grounding electrode conductors are sized based on the size of the transformer's overcurrent protection device, in accordance with National Electrical Code Table 250.66. Bonding jumpers are used to connect the transformer enclosure to the grounding electrode system, ensuring that the enclosure is at ground potential. Seventhly, importance of code compliance. Compliance with the National Electrical Code is paramount for ensuring the safety and reliability of electrical installations. The National Electrical Code is a comprehensive set of standards that outlines the minimum requirements for electrical wiring, equipment, and systems. Adherence to these standards is essential for protecting people and property from electrical hazards. Electrical inspectors play a crucial role in enforcing compliance with the National Electrical Code. They review electrical plans, inspect installations, and verify that all work meets the requirements of the code. By ensuring compliance with the National Electrical Code, electrical inspectors help to prevent electrical fires, shocks, and other hazards. The National Electrical Code is updated every 3 years to reflect changes in technology and best practices. Staying current with the latest edition of the National Electrical Code is essential for electrical contractors, engineers, and inspectors. Continuing education courses and professional development opportunities can help electrical professionals stay informed about the latest code requirements and best practices. Eighthly, practical application scenario. Consider a scenario where a 480 volts to 208 volts / 120 volts transformer is being installed to supply power to a new office space. The transformer is located approximately 250 feet away from the main electrical panel, and the supply conductors are run through a galvanized rigid conduit, or GRC. The first step in grounding this transformer is to install a grounding electrode conductor from the transformer's neutral point to the nearest available grounding electrode. The size of the grounding electrode conductor is determined by the size of the transformer's overcurrent protection device, as specified in National Electrical Code Table 250.66. Next, an equipment grounding conductor must be installed within the GRC to ground the transformer enclosure. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the supply conductors, as specified in National Electrical Code Table 250.122. In addition to the equipment grounding conductor, the GRC must also be bonded at both ends to ensure electrical continuity. This can be achieved by installing bonding bushings at each end of the conduit and connecting them with a bonding jumper. The bonding jumper should be sized in accordance with National Electrical Code Table 250.102 Corn. Finally, a supply-side bonding jumper must be installed between the transformer's neutral point and the equipment grounding conductor at the main electrical panel. This jumper ensures that the transformer's neutral point is properly grounded to the building's grounding system. By following these steps and adhering to the requirements of the National Electrical Code, the transformer can be safely and effectively grounded, protecting both equipment and personnel from electrical hazards. Ninthly, troubleshooting grounding issues. Troubleshooting grounding issues is a critical skill for electricians and electrical engineers. Grounding problems can lead to a variety of issues, including electrical noise, equipment malfunction, and even electric shock hazards. A common grounding problem is a loose or corroded grounding connection. This can increase the impedance of the grounding path, reducing its effectiveness in carrying fault currents. To troubleshoot this issue, visually inspect all grounding connections for signs of corrosion or looseness. Tighten any loose connections and clean any corroded surfaces. Another common grounding problem is a broken or disconnected grounding conductor. This can completely eliminate the grounding path, leaving equipment and personnel vulnerable to electric shock hazards. To troubleshoot this issue, use a multimeter to test the continuity of the grounding conductor. If the conductor is broken or disconnected, it must be repaired or replaced. Ground loops can also cause grounding problems, particularly in sensitive electronic equipment. A ground loop occurs when there are multiple grounding paths between two pieces of equipment, creating a circulating current that can interfere with the equipment's operation. To troubleshoot ground loops, try isolating the grounding paths by disconnecting one of the grounding conductors. If the problem goes away, then a ground loop is likely the cause. Finally, improper grounding of equipment can also cause grounding problems. This can occur when equipment is not properly bonded to the grounding system or when the grounding conductor is not properly sized. To troubleshoot this issue, verify that all equipment is properly bonded to the grounding system and that the grounding conductor is sized in accordance with the National Electrical Code. 10th, grounding electrode systems. A grounding electrode system is a network of interconnected grounding electrodes that provide a low impedance connection to the earth. This connection is essential for safety and for the proper operation of electrical equipment. A grounding electrode is a conductive rod, plate, or other object that is buried in the earth and connected to the electrical system. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The National Electrical Code specifies the requirements for grounding electrode systems in Article 250. This includes the types of electrodes that are permitted, the minimum size and depth of the electrodes, and the requirements for bonding the electrodes together. The effectiveness of a grounding electrode system depends on the soil conditions, the size and type of electrodes, and the quality of the connections. In areas with poor soil conductivity, it may be necessary to install multiple grounding electrodes to achieve an adequate ground resistance. The National Electrical Code requires that the resistance of the grounding electrode system be no more than 25 ohms. If the resistance is higher than 25 ohms, additional electrodes must be installed to reduce the resistance. Regular testing of the grounding electrode system is essential to ensure that it is functioning properly. Ground resistance testers can be used to measure the resistance of the grounding electrode system and identify any problems. 11th, advanced grounding techniques. In certain applications, advanced grounding techniques may be required to provide adequate protection against electrical hazards. These techniques include isolated grounding, equipotential bonding, and surge protection. Isolated grounding involves isolating the grounding conductor from the metal conduit and other grounded surfaces. This reduces the amount of electrical noise that can be coupled into the grounding system, improving the performance of sensitive electronic equipment. Equipotential bonding involves bonding together all metal objects in an area to create an equipotential plane. This reduces the potential difference between the objects, minimizing the risk of electric shock. Surge protection involves installing surge protective devices to protect equipment from voltage surges caused by lightning or other electrical disturbances. Surge protective devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. Advanced grounding techniques should be implemented under the guidance of a qualified electrical engineer. These techniques can be complex and require careful planning and installation to ensure that they are effective. 12th, future trends in grounding. The field of electrical grounding is constantly evolving as new technologies and challenges emerge. One trend is the increasing use of solid-state devices in electrical equipment. Solid-state devices are more sensitive to voltage surges and electrical noise than traditional electromechanical devices, requiring more sophisticated grounding techniques to protect them. Another trend is the increasing use of renewable energy sources such as solar and wind power. Renewable energy systems often require specialized grounding techniques to ensure safety and to prevent damage to the equipment. The development of new grounding materials and technologies is also driving innovation in the field. For example, new types of grounding electrodes are being developed that are more effective in areas with poor soil conductivity. As the electrical industry continues to evolve, it is essential for electrical professionals to stay up to date on the latest trends and best practices in electrical grounding. Continuous learning and professional development are essential for ensuring the safety and reliability of electrical systems. 13th, safety precautions when working with grounding systems. Working with grounding systems can be dangerous if proper safety precautions are not followed. Electrical shock hazards are present whenever working with electrical equipment, and grounding systems are no exception. Always to energize the circuit before working on any grounding components. Use a voltage tester to verify that the circuit is energized before touching any wires or equipment. Wear appropriate personal protective equipment, including insulated gloves, safety glasses, and appropriate clothing. Avoid working in wet or damp conditions, as this increases the risk of electric shock. Follow all safety guidelines and procedures outlined in the National Electrical Code and in your company's safety manual. If you are not qualified to work on electrical equipment, do not attempt to do so. Call a qualified electrician to perform the work. Electrical safety is everyone's responsibility. By following proper safety precautions, you can protect yourself and others from electrical hazards. 14th, documentation and record keeping. Proper documentation and record keeping are essential for maintaining the integrity of a grounding system. Accurate records of the grounding system's design, installation, and testing should be maintained throughout the life of the system. The documentation should include a detailed diagram of the grounding system showing the location of all grounding electrodes, grounding conductors, and bonding connections. The documentation should also include the results of all ground resistance tests, as well as any repairs or modifications that have been made to the grounding system. Accurate records can help to identify potential problems with the grounding system before they become serious. Records can also be used to verify that the grounding system meets the requirements of the National Electrical Code and other applicable standards. Proper documentation and record keeping are a sign of professionalism and commitment to safety. By maintaining accurate records of the grounding system, you can help to ensure the safety and reliability of the electrical system for years to come.